Really?
Yeah.
Wow. Did you tell them?
They said that they're ordering one, but they don't know when they'll get here.
Okay. Okay. I would like to get them to order the smaller copy so it'll be a little cheaper. How many of you still need books? Whoa, quite a few. 1, 2, 3, 4, 5, 6. I'm going to say about 10. Okay. Wow. Okay. We are now recording. Let's see if there are any announcements that you need to be aware. I think we went over just about everything last time. Reminding you I'm on the Birmingham campus on Fridays, approximately 7:45 to 11:45, though there are many days I'm there later than 11:45. And, Samuel, right? Okay, decided he would show up today. Okay. Anyone else come in since I called roll? Okay. Yeah, that's all I can think of. Oh, you would be bothered by that. All right. And for those who weren't here, let me say this. We weren't here last time. Everything we did has been loaded up on YouTube. So if you go to your Blackboard account, okay, for this course, and in the upper left corner, there's a series of tabs. Now on the instructor side, it's like the second or third tab. I don't know what it is on the student tab. It says Content. So if you go to the Content tab and click on it, it will open up and you will see the syllabus. You will see the research paper instructions. You'll see my locator card showing when I'm in class, when I'm not in class, when I'm on campus, when I leave campus, approximately. Okay? You'll see all the PowerPoint for every chapter we're going to do, 1, 2, 3, 4, 6, and 8. And the last thing on there will be your YouTube video link. If you click on that, you'll see a whole passel of videos there. Okay? Go to the bottom. The oldest ones are at the top. Those are ones I've recorded in previous terms. But then go to the bottom and you'll see the ones I've recorded for this term. Now the reason I don't delete them all and start over every term happened earlier this term when my computer died. And then I had to get a loaner from the library. It wouldn't record Screencast-O-Matic, so I couldn't load the YouTube for about a week or two. So therefore, since I didn't have anything to load for those classes that I was teaching, they could still piece it together what we had covered from previous ones. So once I load something that's new material, then I go back and delete the old. So it's only on there once. Okay? All right. Next, please.
Eric.
Huh?
Eric.
Eric, got it. Jackson, right?
Yeah.
Okay. Anyone else come in since I called roll? Okay. So, that's how you'll be able to hear and see everything that we talked about in class. Now, what you can't see is my pointing out things, waving my arms, and that kind of stuff, which I do a lot of, but you can't see that on the YouTube. But the syllabus and everything else is there. A static form is also there in the YouTube video, as well as the PowerPoints. They're there in static form under content, under YouTube videos. You hear me talk about them at the same time because it records video and audio in sync. Now my throat is not in the best of shape, so pretty sure this computer does not have as good a microphone as my other computer, because when I've heard some of them, they're a lot weaker than the old ones were. It says it's getting a good signal, but I can't tell that when I listen to it, it's not as good a signal. All right, any questions from anything we've done so far? All right. We started this last time, this is chapter 1. This is the second part of chapter 1. The first part was talking about things like measurements and objects and things like this. Now we're looking at the nature of science, which is sort of a nebulous, just general discussion. However, you might see some potential things here for paper topics. Of course, science has always been here, but mankind hasn't really understood science or studied science as a science until fairly recently. The beginnings were about 300 years ago. Now, sure, before that, we had what they called the natural philosophers. People like Democritus in Greece, and Aristotle in Greece. In some senses, Plato and Socrates too. They were more philosophers than they were scientists, but they called them natural philosophers, okay? Which included. And for many years, Aristotle was king. I mean, everybody thought if he said it, it had to be true. I mean, for centuries, for millennia, everybody just assumed whatever Aristotle said, that was it. Okay? Along came an Italian named Galileo. His first name is almost the same as his last name. And he started questioning some of the things, precepts and things that Aristotle had just stated as fact. And in testing them, he found out some of them were okay, but some of them were off. Okay? The process of testing, experimenting, in some sense being skeptical about it, that started science, what we call today science. The very year that Galileo died, a young Brit was born, Isaac Newton. He continued Galileo's work and expanded on it big time. So those are two potential paper topics. If you just want to write on people, those are two. Now, here's the deal. I ask you to turn in pages with your paper topics on it. First come, first serve. First Galileo, that's it. No more Galileos. First Newton, that's it. No more Newton. So get your topics in early so we can see. So the others I mentioned are also potential topics. The ancient natural philosophers I was talking about only sort of thought through. They looked, they observed, they thought and said, this must be true. Okay? They were pretty good at it, but they didn't test it. The additional component here is understanding based on experimental evidence. That's what science is, as opposed to just observing things. All right? The scientific method has sort of emerged, been modified, but grown over time, and it basically started with Galileo. Observe some aspect of nature. That's what the natural philosophers did too. They've been doing it for a long, long time. Okay? But observe some aspect of nature, then propose an explanation for something observed. Aristotle and the ancient philosophers had done that for centuries, millennia. Okay? They had all done that. However, what Galileo's contribution was, use the explanation to make predictions. Okay? Well, then if we do this, this should happen. Let's see it. Number 4. This is really where it comes into play. Test those predictions with experiments and more observations. See if they fit the bill. Galileo did this with many of Aristotle's ideas, observations, suppositions, and found, nope, they didn't hold water. They weren't quite right. They were okay to a certain limit, but not. So he started experimental science. Modify the explanation, your prediction, whatever you think is going to happen as needed. Go back and make more predictions, test those new ones with more experiments, more observations. Even when you get something right. Okay, well then, if I did this, would this still happen? And this is how science has evolved, grown, matured, and expanded for years. And experimenters are still doing this. My wife's epidemiologist at University of Alabama at Birmingham, UAB, and she does this all the time. She writes grants to, okay, we understand this, we think we understand it pretty well. What would happen if we did this? Or can we dig a little deeper into that? You know, that's what scientists typically do. Okay. Here's sort of an example. What are atoms made of? Of course, an English instructor would probably say you should never end the sentence with a proposition. Okay. Of what are atoms made? Okay. Of course, this couldn't have been asked way early in the game because people didn't even know atoms existed. However, long before Aristotle, Democritus proposed that they did exist. Okay. Again, it was just by thinking, what they sort of call now a thought experiment. And here's what it was. We'll hit it again later. He just imagined that he had a piece of iron, say. Okay, let's break or cut the iron into two pieces. And then cut the smaller one into two more. And then smaller into two more. Just keep going down. He said, his thought experiment, is there some point at which, when I break this down smaller and smaller and smaller, that I hit a particle that can't be broken any smaller? He said it must be true. I don't see any way around it. Of course, he couldn't do it. He couldn't even come close to it. But his thought experiment was, yeah, you have to reach some limit and say, that's it. That's as small as you can go. The Greek word for indivisible is where we get the word atom. Okay, he proposed this. And in a couple hundred years, here came Aristotle and said, nah, all matter is a continuum. You can't get the smallest piece. It always, no matter how small it gets, it's still iron. You can keep going ad infinitum. You know, it's a continuum. So he basically chucked out Democritus' proposal. It was just a thought experiment anyway. And everybody thought from then on, because Aristotle said it, there must not be anything. Well, many years later, and we'll hit this several times, especially in the chemistry chapter, they came up and said, you know, there's got to be some smallest particle of this, otherwise things just don't work. And John Dalton came up with the atomic theory. So this question could have come after John Dalton's atomic theory. This is probably 17 or 1800s, somewhere in there. AD. Aristotle was BC. Democritus was earlier than that, BC. Okay. Here is the idea. What are atoms composed? Negative electrons orbiting a positive nucleus. Okay? Well, how would we test that? Well, let's get those atoms, accelerate them like crazy, and have them collide with each other. If that happens, there should be some electrons thrown off, okay? And maybe some isolated nuclei. Let's see if it works. So colliding two atoms yielded, sure enough, got these little negative electron charges there. And you saw that you also had in the nucleus other objects called protons and neutrons. Now, if they broke that apart, they actually had a nuclear reaction on their hands. And that probably, I'm guessing, is how the first fission reaction occurred. Someone was saying, hey, what would happen if we did this? And then suddenly we had a nuclear incident. Okay, probably on a very small scale. So atoms, the conclusion here, atoms are made of electrons orbiting a nuclei. The nuclei are made up mostly of protons and neutrons. Over the decades and probably centuries since that concept came to play, they found there are even smaller particles in there that have some sort of functions. They don't even know what. They call them positrons and neutrinos and all sorts of other things. But as they keep digging, they keep finding. Well, let's go out at higher energy and see what happens. And that's where they came up with some of these other elementary particles. And there's a whole branch and field of physics now called elementary particles, where you just keep colliding things as much as you can. You have to develop the equipment and the technology to measure these very tiny events. And if you got that done, try to figure out what happens. Here is typically what has occurred when you follow the scientific method. I'm going to use physics as an example because I was a physics major undergraduate. And around the late 1800s, early 1900s, physicists in general thought, we've just about got it all tied up. Newton's laws of motion, they summed up things pretty well. William Thomson, laws of thermodynamics, they got that one tied up pretty well. Every field they had a pretty good handle on. There were just a couple of little nagging questions. They hadn't quite figured out why they saw something or occurred. But we can do it. We've got the rest of our lives to answer these 2 or 3 little nagging questions. So they started looking into those and discovered an entirely new field of quantum mechanics. Okay? And everything they thought they knew before was pulled into question, because if you get on a small enough scale, Newton's principles of motion just didn't seem to work anymore. So on quantum mechanics scale, they had to come up with brand new things. The more they found out, the more cans of worms were opened. Okay, the more places they could investigate. And that is typically how it goes. You answer one question, it usually opens up 3 to 4 more. Okay, y'all heard the Greek mythology. What was it? Odysseus, in the Odyssey. He was traveling around trying to find his wife. I think that's what it was. He ran across this monster named Medusa. She had a head full of snakes, and every time you cut off a snake,
Correction, I don't think that's Odysseus. I think that's Perseus that
was it Perseus?
That killed the monster Medusa.
Okay, it may have been. Because every time you cut off a snake, 2 or 3 more grew where the one was. So it just kept getting worse. So he found out he had to get a thing of fire and burn them, and they wouldn't reproduce it. So that may have been Perseus. I was thinking it was one of the trials. Whatever. Well, that's how has been with science. As soon as they think they get one thing answered, whoa, look at this. There's a few other questions that pop up. And that's where we really do our learning. Almost as much from the mistakes as from the intentional. You've heard the story of penicillin, right? Someone was trying to study bacteria, study how they grow and blah, blah, blah. And I don't know if it's something as simple as he was eating lunch in the lab and didn't realize, but a crumb of bread fell onto the media that was growing the bacteria, and they all died. What has happened here? Well, one of the bacteria that lives off bread is one called penicillin. One of the substances, it's a mold that lives on bread, produced a product, a byproduct called penicillin, and that killed the bacteria. Yeah. Huh?
Does mold live on bread?
You've never left any out too long?
Well, I have.
That green stuff?
Yeah.
Yeah. Now, all of that is penicillin, but some of it is. And the penicillin will kill. Because of that, the whole field of antibiotics came into play. Before that, people died more of infections than they did just about anything else. Nowadays, infections are low, people still die from them, but usually they have immune problems or something, or they don't get treatment in time. Okay, so quite often the scientific method has advanced both by thoughtful discovery, but also by accidental discovery when something didn't quite go the way they were expecting. So here's the general scientific activity. Just like the ancient Greek philosophers and others, and we're focusing mostly on the Greeks because that's Western thought. The Chinese were doing it probably before the Greeks did. The Babylonians, the Sumerians were doing it probably about those same times. So there have been many times, but all have been collecting observations and developing explanations. Aristotle did it, many did it. But for like Galileo and later Newton and then the whole field of science since then, testing those explanations to see if the ideas you had really were the reasons those were happening. That's the part that modern day science happened about 300 years ago and has been happening ever since. So, how do these things go? Typically, you start with a hypothesis, okay? I'm going to try to get this fairly simple example. When I was at the University of Georgia doing agricultural research there, my major professor for whom I was working was in soil fertility. Okay, so he was trying to determine what were the rate limiting factors in, say, growing corn in this particular kind of soil. Well, one thing was obviously in a lot of the soils in Georgia and the southeast, not as much in Alabama, were very acidic. Okay, so they found out they had to lime the soil in order to get the pH to come up some to do. So his hypothesis was corn's not growing well, producing yield because of high acidity. So the experiment, let's recreate the event, that's not recreation, that's recreation of an event or occurrence to test the hypothesis. So we had this area of land that had all pretty much the same kind of soil and split it into plots and even split the plots into plots, okay? And then we would treat this particular area with no lime, put no lime on it. This one put a little bit, this a little bit more, that a little bit more. See the results, okay? Now, that was the setup. This is a controlled experiment comparing two situations. I just named several. Let's just say lime or no lime, okay? So the control situation would be no lime, okay? That's the fit set. Now, of course, if there's no nutrients there, it's not going to grow anything. So let's fertilize or do whatever other treatments, tilling the soil the same way, adding fertilizers the same way, adding water at the same rate, do everything else that we can exactly the same, and only could look at one difference, lime or no lime, okay? And the control group is the one with no lime. The experimental group would be everything else exactly like the control group except add a certain amount of lime, okay? See if it made a difference. And generally, it did big time. But then they found out once they got the pH right, then the rate limiting step may have been something else. Was it enough phosphorus? Was it enough potassium? Did you have enough nitrogen? What were the other things that would have done it? So once you got one thing answered, there were many, many other questions. That's what we mean by a controlled experiment. My wife studies a certain virus called cytomegalovirus, okay? And her doctoral research, I would say, was focused on this. Is CMV, cytomegalovirus, spread by sexual transmission? And her hypothesis was it would be, and she didn't do an experiment, but she studied medical records of the births in the hospitals over many years. Those children that were born with CMV as opposed to those not born with CMV. So what she did, she knew the ones that were born with CMV, they had documented that, so she went back through the records and found, if as close as possible, another child born on the same day, same gender, same race, much as possible, same socioeconomic situation. I think she used whether they had insurance or not for that one. She tried to get everything else the same, except one child had CMV, the other didn't. Now, for the mothers, she had to have medical records that the mothers had had treatment ahead of time. She found out if they had been treated for sexually transmitted diseases or not. Had they had counseling or not. Had they recorded that they had multiple partners or not. And she did her research and found out, sure enough, which she controlled for everything else she could except sexual activity and whether the child had contracted CMV. Found out pretty good correlation. Other studies were done. Her boss had done one on infants in daycare, because that's not the only place that you could get it. They found out that mothers who had a child in daycare, the mother may not be CMV positive, but the child picks up CMV at daycare, brings it home, infects the mother, she's pregnant with the next child has it. So, yeah. So there has been, and my wife has spent most of her career studying that one virus. Now, she's done some influenza studies, she's done a few other things like that, but most of it has been cytomegalovirus. And the more you find out, then the more questions. Well, if that's true, would this work to prevent it? She's doing a study now, or has been doing one, on when mothers are counseled, here are the things you can do to cut down the possibility of getting an infection from your other children. And she collects the data from that and sees if their intervention has had any good. They do clinical trials, trying this antiviral, that antiviral. There's a lot of things they try to do to either prevent the disease or deal with the disease. And one thing they've learned, one of the major sequelae is what they call it, results of having CMV, is the child has a higher than normal chance of having hearing loss. She thinks I must have had it when I was a child, okay? But no way to go back and find that out. But they found out if they can discover the hearing loss early, they can start interventions early, and the child can adapt and not be totally deaf. Because children adjust far more quickly than when they're young than when they're older. When you get my age, you don't adjust at all. Okay, so that's explanations and other words. Now, this author almost goes overboard on what he calls pseudoscience. Does anyone know what the prefix pseudo means?
No.
Anyone know what a pseudonym is?
No.
No. Say again? It's what?
Alternative?
Okay, almost. Okay? It's like a pseudonym would be an author. And this happened back when women weren't supposed to be educated. And they certainly weren't supposed to be good writers. But some of them were very good writers. And they would have to put their name like, there's a mystery writer I can't remember what she went by, but she used initials and not her first name, because if she used her first name, they'd realize she was a woman. So she just used her initials. Others just made up names. And I can't think of any of them right now. There was another, I think he was a doctor or somebody who was really a prestigious person, but he had kids and he wrote kid stories for them, okay? But he didn't want to damage his prestigious reputation by be associated with children's books. His name, I think, was A.A. Milne or something like that. Wrote the Winnie the Pooh series, okay? I don't know if any of you have ever heard of that, but quite good children's book, but he didn't want to be credited with it. Actually, the woman who wrote Harry Potter.
J.K. Rowling.
Yeah, I think that's one of the reasons she went by initials J.K. rather than what her name was, because she wanted to be taken seriously as a writer, and she thought if she put her name there, they wouldn't.
She wasn't taken serious on most of her early books.
Yeah, exactly. And so when she became innocuous and they didn't know that she was a woman, suddenly she was a great writer. Whoops, you're a woman. Okay, so unfortunately that happens. So pseudoscience would be fake science or untrue science, or not quite there. He calls it misleading and often absurd claims of scientific results. About half the internet is filled with this. Pseudo something, okay. So, how do you distinguish the real science from this stuff that sounds pretty good, or at least plausible, but has really no basis in fact? Here's some things he suggests. Look at the academic and scientific background of the claimant, okay? If it's someone you've never heard of, there's probably a pretty good chance this is blowing smoke. Now, there could be some unknown brilliant people out there, so that's at least one. What are his academic credentials? Where has he studied, or she studied? What is his or her scientific background? Second, history of review by scientific peers. Now, this is almost a cutthroat business. Anything that's submitted for publication in official publications has to be reviewed, I'm pretty sure of this, by at least 3 well-recognized experts in the field. If you send something to a journal, New England Journal of Medicine, Journal of American Medical Association, those are ones that my wife has published in before, but any journal, or most journals, most of the good journals, they receive your thing, they send it out to, again, at least 3 reviewers. They have these reviewers on call. They call them up, can you review this paper? It looks like it's in your area. No, I'm too busy right now. Oh yeah, I've got time, I'll review it, And then they do, and sometimes they can be really nasty about it. Oh, no, this isn't as good as my work, or something like that. But most of the time, they're really good reviews. And you get it back and all these comments, because everybody, especially when you get that high up, they have opinions and they think theirs are the best. So you have to accommodate those to some extent, and generally you do improve your paper. And then you send it back out, and if it meets what they required, then they'll publish. That's what they mean by scientific peers. Review by scientific peers. Most of the good legitimate journals require that. Participation in scientific institutions and organizations. Most of your better scientists are either associated with universities, research labs, or something of this nature. Very few are out there flying, Lone Rangers flying by themselves. They just don't have the resources, and they don't have the interaction to really do as good as science generally. Okay? And then number 4, plain published in peer-reviewed journals, which frankly it sounds a lot like number 2, and independently validated by others. Okay? Now I talked about sometimes the papers are sent out for review. if it's a new process or procedure with great claims coming out of it, not only do they send it out for review, they send to a laboratory or a university or somewhere like that and say, look, we'll pay you to reproduce this experiment. And if you get the same results, we'll publish the paper. If you don't, we've got to figure out why. Because this sounds too good to be true. And you've probably heard the saying, if something sounds too good to be true, it probably isn't. But a few things have been. But they actually go out and independently validate whether you can reproduce this. If it's not reproducible, it may have just been a fluke. It may have been a crumb of bread, spread some mold on your petri dish, and that's what killed the bacteria, not you're saying these words over and on. Okay? So, this guy is a little overboard with pseudoscience, but it is something to keep in mind, especially if you're using the internet as sources, especially then. All right, well, how is science put together? We have things called laws and principles. Now, there are no clear litmus tests. Oh, this makes this a law, that makes it a principle. This is a continuum kind of thing. Generally, your laws are important relationships observed to occur time after time after time. You throw a ball into the air, it's going to go up, slow down, stop, and fall back again. We call that the law of gravity. Okay? It happens every time. Okay? Important relationship observed to occur time after time. It's usually just descriptive in nature. It can have quantitative features as well. Here's an example. Charles's law. Relationship between temperature and pressure in gases. And this guy's last name was Charles. I don't remember his first name. But he said that if you control the volume and increase the temperature of a gas, then the pressure is going to increase. If the temperature drops, the pressure goes down. Last night I went out and tapped off my tire. One of my indicators, I've got it RAV4, said I had a low tire. So I went out and checked, and yeah, sure, something on the low. Well, the temperature's dropped. So I went and checked them around. I think I have the bad sensors because I've got every tire up there and the light's still on.
Is it flashing?
Huh?
Does it flash?
When I turn on the key, it comes on immediately, then it goes off, flashes, and it stays on. What's that?
Got a bad sensor.
So it like blinks at you.
It doesn't blink, it just stays on.
So it goes off and then comes back on and stays on.
Yeah.
It's probably your spare.
The spare, okay, it could be. Okay, I forgot. Yeah. But sure enough, 2 of my tires were low, 2 of them were fine. But no matter what I did, I couldn't get the light to go off. So you're right. I forgot they have that.
You have to reset the light.
What's that?
You have to reset the light on the RAV4s.
Can you? Okay, I need to do that. Okay. All right, but anyway, you realize that, okay? So when is a terrible time to check your air pressure in your tire? Right after you've been driving for about 50 minutes on a hot road in the middle of summertime. Don't check it then. Probably going to be high pressure. Wait till it cools. That's when you should be checking. That is a law. Okay, it always happens. When I was living in Nebraska, when I was doing my doctorate in Nebraska, there was a lady at our church who, she and her husband had divorced, and he moved to another part of the state. He didn't have much time to spend with his son, so she just asked the guys at the church if anyone would, spend some time with him. She felt like he needed a male, figure there. And I was single, and I thought, I have nothing, can't contribute anything there. So, Chelsea's here. Later we were playing, he was a good athlete, and I played on the church softball team, and he came out to play too. He was early in high school. He was really good. So I really encouraged him a lot, and we became pretty good buds. So I thought, well, probably would decide to start going over, doing some things with him periodically. And went over one in Nebraska. It got cold way early in the season, and he had left his basketball out one night. He'd been shooting a few hoops, left it out. And that Sunday afternoon I went by, and it was a pretty cold day. So he said, let's shoot some hoops. We went and picked it up. He said, oh, I have a flat. I must have punctured it. I said, no, take it inside. Let it sit there for a while. We'll do something else. See, took it inside, and about an hour later, said, go get the ball. He did. It was not flat at all. It was regular stuff. If he had pumped it up then, and then later taken it inside, it would have probably been overinflated. So, Charles's law. That's a law. Always happens. Sort of descriptive in nature. Now, how's that different from a principle? Not a lot of difference. Principles are also descriptive in nature, but generally a little more specific. Okay? Now, what differentiates a law from a principle? There's not much. I mean, some people may call the principle of buoyancy, they may call it the law of buoyancy. Okay? It just depends on where you draw the line. There's not always a clear distinction between the two. And that's what this is. Archimedes' principle relating objects, fluids, and buoyancy. Sometimes it's called the principle, sometimes it may be called the law of buoyancy. Here's one. Bernoulli's usually called the principle. And you're probably, whether you know it or not, have interacted with this before. What would happen if I were to blow on the underside of this piece of paper? Any ideas? It'll go up? You're right, it does. What if I blow over the top of this piece of paper? What will it do? Uh-oh. What in the world happened there? Bernoulli's principle. Okay? And you've all experienced this, I bet. Okay? Any of you driving down the road, this big 18-wheeler is barreling down the road, and you decide to get over maybe in the next lane or behind them. Sometimes you get too close, and you draft on them. Bernoulli's principle. Anytime the velocity of a fluid, now this is a gas or a liquid, increases, it drops in pressure. Okay? That's Bernoulli's principle. And that's what's happening with the plane. The air around him is really going a lot faster, so the pressure's less, and it sort of drags you along. Don't they do this in NASCAR? There's a team always has a sacrificial driver, right, out there leading and letting the honcho draft on him for most of the race, and then toward the end, the guy they want to bring home the bacon takes off and does it. They do this in runners. If you watch the Olympics or any of the long distance running, always someone's setting the pace and others are just following, but then at the end they go zooming around. He's breaking down the air resistance, but they're sort of drafting on it. It's not a large amount, but it's a little bit. Okay? So, some people might call that a principle. I think most people call Bernoulli's principle not a law, but there's not a lot of difference between them. Okay. We also have other distinctions here. One is called a theory. And we sort of were introducing this earlier. A theory is a broadly based set of working hypotheses. Okay? These are ideas. Okay? These are things we're trying to test. But we don't know if they're true or not. Okay? They're a theory. They could be based on considerable experimental support, but it's not yet a law or a principle. It's still just a theory. They form the framework for your thought and experimentation. Here you come up with a new hypothesis. You test to see if this theory might be true. The Big Bang Theory, it's always going to be a theory. You can't go back and reproduce it. Okay? So it's just their best idea based on the working hypotheses they have now, considerable experimental support. The framework's there. How are you going to test it? You can't. So it'll forever be a theory. Don't want to get too dangerously close to controversial issues, but the theory of evolution is just a theory. I mean, you can't go back and start with those two little organisms and and retest and see if Leakey, whatever his name was, Leakey, I think it was, did a lot of that early work. He proposed the theory, but most of it can't be reproduced. Start over. Now, we also have things called models. These could be a collection of theories or ideas intended to represent a physical system. Okay? Now, quite often they're useful for regimes either too large or too small or too vast for direct observation. For instance, the Big Bang Theory. You can do all sorts of modeling of it, but you can't really go back and produce the universe. Okay? They can be physical or they can be mathematical. Okay? I'll give you sort of an example of both. Remember the theory of the atomic theory? I said John Dalton. The chemist, the field had been developing over time, had noticed this thing, that materials combine by what they call the law of definite proportions. If you had 5 grams of hydrogen and, let's get something better, 18 grams of hydrogen and 16 grams of hydrogen and 16 grams of oxygen, okay? And you went to combine them, it would combine 16 grams would combine with 2 grams. No, 4 grams. Always. You always have hydrogen left over. If you had 2 grams of hydrogen and 16 grams of oxygen, then 8 grams of oxygen would combine with the 2 grams. You would have oxygen left over. They always went by the law of definite proportions. Well, John Dalton said these things, like oxygen, it always combines generally with 2 things, or in 2 ways. So he said oxygen has 2 little hooks on them. Okay, that was his model. He knew pretty much it didn't have 2 little hooks on them. But this was his model. Hydrogen has 1 hook. Okay? And the hydrogen hooks to this one, but another hydrogen hooks to that one, and what do you have? H2O, water. And they always combine at that ratio. Okay? Whereas carbon has 4 hooks. Oxygen has 2 hooks. These 2 do 2 of those and 2 more of that, and what do you have? Carbon dioxide, of course. And they always combine that way. So he came up with, that was his model. He pretty much knew they didn't have hooks, but they combined as if they did. So that was his model, a physical model. Now we know what was happening. They have free electrons. And carbon has 4 free electrons, oxygen has 2, hydrogen only has 1. That's what it was. Well, that's not quite it, but it is somewhat similar to that. Oxygen actually has 6 electrons in the outer shell. It wants to have 8, so it wants to have 2 more. So it steals those from hydrogen. Yeah, so that kind of thing is happening. That was before he could know that. That was his model. Now, a mathematical model. A guy named James Clerk Maxwell. It's spelled Clerk, but it's pronounced Clark. He was Scottish. They pronounce things strangely. Okay? He had been studying electricity and magnetism. People knew suspected there was sort of a connection between the two, but they didn't know what it was. And it was way before they had the technology to do it. So he studied it mathematically, and he came up with, I think it was 4 laws. They're called Maxwell's equations. they were hairy equations too. He said, this follows this, he had basis for it. He came up with that model. It was, I think, about 70 years later, finally the technology was there to test it. And they found out those 4 equations fit like a glove. He was way ahead of his time, but he thought through the issue and said, that's a model I think ties these together. And sure enough, we know today. Y'all use magnetism and electricity together, don't you? You have in your generator, charging your battery, okay? Yeah, there's a magnet in there. A moving charge creates a magnetic field. A changing magnetic field induces a current, okay? He came up with it way before we could even come close to that understanding. All right. In fact, I may have already passed it. Sometimes I get talking too much. Yeah. Back on page 15, there's a little blurb. Now, this book is full of little blurbs, okay? And they usually color code them. This is called Science and Society, and it's basic versus applied research, okay? For instance, James Maxwell was basic research. He thought through the issue, he came up with the equations and stuff like this. Later, applied research, well, can we make a generator out of this magnet? Can we produce that? Sure enough, they found out they could, So, basic versus applied, or basic and applied research. A nice little blurb to read, top of page 15. There are actually some questions there. In this case, probably you wouldn't find paper topics on that. But if you're really interested in wanting to pursue it, perhaps you could. Okay? And here's Ashlyn. Okay. There's a little blurb, these are sort of the beige ones, that say seekers of pseudoscience. Read that if you want to. There's one called the Science Sketch. Yes?
You're on page 15?
I'm sorry?
You're on page 15?
I've already moved off of that now. Yeah. Page 15 was the basic and applied research, top of the page. Page 17 has the seekers of pseudoscience, and then a science sketch. We had already talked about the stuff that's there. I just hadn't turned my pages to keep up. All right. Here's a model. People throughout history have observed that sometimes, not always, sometimes after a rain, you'll see a rainbow. Okay? I think you can probably see that from where you sit, but if not, if you got a book, you can see it even better. Okay? And not often, but occasionally, you can see 2 rainbows. Okay? Now, their relative shapes and distances apart always seem to be about the same. Okay? Now, what are some things you note about rainbows? If you can remember the last rainbow you happened to see, did you notice anything about it?
They tend to fade.
Say again?
They tend to fade.
What?
They kind of fade.
It fade, yeah, it would fade over time, for sure. You remember what time of day you saw it?
Afternoon.
Afternoon. I bet you the vast majority of rainbows you'll ever see are going to be in the afternoon. You might see a few in the early morning. You'll, I want to say, never see one around noon. Okay? Now, why do you reckon that would be the case? The sun has to be, the other thing you note, when you see a rainbow, the sun's behind you. Every time. Next rainbow you see, look for the sun. It's going to be behind you. If you're looking at the rainbow, the sun's back there. Okay? So this is indicating, these are indicators, there must be some science here. Why does this rainbow form? And why does occasionally you'll see a double rainbow? Now, you tell me something you noticed about that double rainbow.
Nowhere near right.
Which one?
The second one.
The outside is not nearly as bright as the inside. Very good.
The outer one mirrors the older one.
And what do you mean by that?
It's backwards.
Yeah, the colors are backwards. The red's on the outside here, it's on the inside here. Very good. Green's on the inside here, on the outside there. Okay? What could be going on here? Okay?
No, that's a different one.
Here is the idea. They think this is the result, and the theory is, the model is, it's a result of reflection and refraction. Okay, and it always happens after a rain, right? That's obviously the other thing, rainbow, after a rain. Why? Because there's water droplets in the air, okay? Just suspended in the air like that. You'll never see one on a dry day, ever, okay? Especially at noon, okay? So, they think this must be the result of reflection and refraction. Now, does anyone know what reflection is? You use the term mirror, okay? It reflects light. Light is bounced back at you. How about refraction?
The distortion?
Kinda. It's bent, okay? Have you ever stood in a pool of water and looked at your legs or looked at someone else's legs? They look a little weird. They look like they're bent. They look too short, yeah.
Isn't that model for when you put a pencil in a glass of water and it looks like it's broken?
That's it, exactly. That's exactly what I'm talking about. The light is being refracted by the water, as it is in the little water droplets. So here's the theory, okay? And the sunlight, if the sun's so far away, we think of it coming in parallel rays, okay? Good assumption. So the sunlight comes in parallel. Now, if the sunlight comes in here, it's going to go right through a droplet, up here. Yeah. But if it comes in right here, at a certain place, which is, we'll get to that in a second, the water has a different index of refraction than air does. So it indeed acts like a little prism. And all white light is made out of these colors: red, orange, yellow, green, blue, indigo, and violet. I don't know what indigo is. I think they put it in there just so they could spell Bibb, Roy G. Bibb. Otherwise it would be Roy G. Bibb, and they wanted to have that violet in there. But there is a color indigo, but I don't know what indigo is. It's not blue or violet. Okay. So anyway, it splits it into that. Now, at a certain thing, down here, the light, it just goes through. Here, it refracts the light, that's the bending of it, refracts it, and it hits the back side of the droplet at a specific angle. This is called a critical angle. And at the critical angle, the light doesn't go through, it gets reflected. Okay? And then when it gets reflected, this shows that it actually reverses, the color scheme, because when you're reflected, and you used it before, it mirrored the other one, things are reversed, okay? And it comes out and then is refracted again, and this is what you see. You see red, yellow, orange, yellow, green, blue, indigo, and violet, okay, coming out. And these are always at 42 degrees. If you see a rainbow and happen to have a sextant in your hand, which of course you would, put it at the center of that rainbow and measure that. It's always going to be 42 degrees. Always. Okay? So that's the idea. However, some sunlight comes a little bit further up, okay, or down, either one, but a little bit further up, and it also refracts. What do you call that? Goes into a spectral. It hits the back of the drop and is completely, it's called total internal reflection again. The angle is just right to do that. But then it's so far down here that it reflects again and comes out, and this is what they're, and both times it mirrored or reversed the rays, so the second time they come out in exactly the opposite order, which is what you observe here. And this one is more intense because more light goes through that part of the rain droplets than goes through this little bitty part up here. Only a little bit of light gets that double reflection, and that's why it's so hard to see. Okay? So sure enough, this model explains the displacement. And by the way, this is now 51 degrees. So if you were to measure the angle between that, it's always very uniform. It's a difference of 9 degrees between the two rings. Always reversed order. That's total internal reflection and refraction. Got it. Done. So that's an example of a model. Your book gives another one that we don't have a slide on, and the folks that were in Physical Science 111, you've heard of this one. It was called Continental Drift when it first came out. People looked at, and there's not a slide for it, so I'll just hold this up for people who don't have a text to look at. People looked at the countries on either side of the Atlantic, and notice how North America has a bending up here, but Europe bends up the opposite way. Okay? South America has a hump here in Brazil. Africa has an indentation there around the Congo or Cameroon, around in there. And they said, you know, and Africa's hump almost looks like it could go into the Caribbean and Gulf of Mexico. And people said, you know, I wonder if those were originally joined and the continents are drifting apart. Okay? When someone came up with that idea, people said, are you nuts? Continents don't move. They're huge. They're fixed. They can't move. They were laughed out of town until, I think it was around World War II, the U.S. Navy and other people were doing study. I mean, what did they have in World War I that was giving everybody fits crossing the Atlantic?
Submarines.
Yes, they called them back then the U-boats, and they were sinking ships. You know, we were trying to supply Europe with goods, food, you know, other things, so they could fight the war and we could stay out of it, and our transports were getting blown out of the water by the U-boats. So we started studying and seeing if we can, you know, use sonar and other things to detect. Well, sure enough, as we found out we could study the bottom of the ocean. So people started doing that, and lo and behold, found out there was a ridge right in the middle of the Atlantic. And sure enough, they found there was some temperature there that was unaccounted for. They found out there was volcanic activity there. And that indeed, the plates, and this is when they came out with the concept of plate tectonics, you may have heard of it, were actually moving apart. And since they were moving apart, sure enough, Europe, Africa, North South America were moving apart. They could have at one time been one big continent. Pangea, they called it. Okay? We don't know that it ever was, but we do know they're drifting. And they've done more and more research and found out, sure enough, there's layers of iron ore been deposited, and they match on either side, but they don't match the other. And sure enough, different layers. This is newer rock here, newer fossils here, older stuff here, older fossils. Everything seems to match. Okay? So there's another theory that people thought was outrageous pseudoscience and turned out being, nowadays, what reality is. All right. Now, I know some of you have been getting your books, some of you don't have them yet. I hate that. They said they had ordered more, but they didn't know when they're coming in. Is that what you were told?
Yeah, one thing I just want to say, you said you had the 11th edition, right?
Yeah, but either edition will work.
Well, our 10th edition, the pages are not the same as
What's this again?
The editions that they're selling in the bookstore, the 10th edition, the pages are not the same as the ones you
Yeah, the page numbering is not the same. Yeah,
Right.
that's why you were asking that earlier. Yeah, but the content is basically the same. They've added a few more pictures or a few more blurbs in it, but really the content is. I taught from, I can't remember the first edition that I taught from. It seems like it was 8th or 9th or maybe even before that, and the content really hasn't changed.
I bought the 8th edition for like $30 on Tag, and it's all the same. It's just the page numbers are different.
The page numbers are different, and the colors are different. That kind of silly mess. Have I given you what my theory is on that?
Yes, sir.
I have given it.
Currency.
Huh?
Just trying to make money.
Of course they are. The publishers only make money when they sell new books. So therefore they require their authors to come up with new editions every 3 to 4 years so they can sell more new books. And it doesn't have to be very much change at all. Usually it's just color and presentation. Yeah.
So what does yours say the name of chapter 1 is, just so we can find it?
What is science? I think it is. What is science? It's the name of chapter 1. Okay. So we're ready for the first test. That will be Tuesday. So try to borrow a book, share books. I've got at least one. I've shared mine out, all the spares I had, and I didn't get some of them back, but I do have at least one spare little thin book, but same as this. So if anyone needs it to study over the weekend, I'll be glad to get it. I do need it back though. Yeah. What's that? Oh yeah, you can have a formula and equation sheet for every test you take, including the final exam. So yes, so put that together. Go back and listen to YouTube, whatever it takes. The best thing would be to read the chapters. So that's why I say, see if you can bum, beg, borrow, steal a book, not steal a book, okay? Use somebody's book, no matter what edition it is, see if you can get that.
You gonna come get me out of jail?
What's that?
You gonna come get me out of jail?
Oh, no.
All
Alright. Okay.
You gotta still another one, third one.
Yeah. But, see if you can share and that kind of stuff. Once you've read the chapter, in fact, now this part I didn't have to do that much, but the first part of physical science, which is the second part of this book, the astronomy part, when I had to teach that, I had never had an astronomy course in my life. So I read those chapters over and over again to make sure I understood them well. Now, you don't have to do them that well, but I would say the guy doesn't write at a super simple level. It's simple enough. It's understandable. But for the astronomy part, I read those chapters repeatedly until I felt really comfortable about it. You don't have to do that many, but I would definitely read the chapters if you could. In fact, it's best to do them ahead of time, ahead of the lecture, and that way I think the lecture will make a lot more sense. Not that I'm lecturing. Then there's a summary, okay? The summary, this one is a bit on the short side, maybe about normal. But on the same page as the summary, page 20 or somewhere thereabout, there's people behind the science, Florence Bascom. And frankly, I don't think I'd ever heard of her before I started teaching from this book. Nice little blurb there on her. Nice little blurb. She would be a potential paper topic. But guess what? This cannot be your source. The book is not your source. You can get the idea from here, go and get your sources from elsewhere. If you read very much of this, you will see that you'll probably run across some other names that probably were quite influential as well. One I see right here is Johns Hopkins, okay? So there's a lot you can get out of some of these blurbs as far as your paper copy. Now, summary of equations, this chapter only has one, uno. That was your density equation. I would say that was probably pretty important. But remember, we showed two different equations than this one that express the same thing, solving for mass or solving for volume. So actually there's three equations there, even though they only listed one. Then there's key terms. Now the key terms are listed alphabetically, but they do give the page number where those key terms were either defined or described at first. Now, here's the other thing. If you have your book, the next thing at the end of the chapter is applying the concepts. 44 multiple choice questions. Now this chapter is probably a little bit lighter than most. Most of them are closer to 50. This is pretty close. They have the answers listed there. I would definitely, if I had a book, this would be a great way to study for the test. Read these. You try to come up with your best answer. After you come up with them, then compare the answers. If you missed any, go back and figure out why you missed it. If you can't figure that out, bring it to class and I'll be glad to work with you on it. Okay? You can all learn from it. Okay, then there's questions for fault. There are only 10 of those. That's a bit on the short side. There's 7 for further analysis. That's actually more than most chapters have. And then there's Group A parallel exercises at the end. The parallel exercises have the Group A have answers in the back. Okay? The Group B do not. So I would say try to do some of those Group A. Of course, number 1, they're not going to have an exact answer there. What is your height in meters? They don't know how tall you are, so they can't have that, but they may give something else. How about the centimeters? So anyway, those are good things to study for the test. So let's go over this. We just finished chapter 1. At 5:45, we will have the lab on chapter 1. I've got the copies of it right here. We'll go right down the hall here in room 253, as long as there's no biology class in there. If there is, we'll move across the hall to 252. If that was occupied too, we'll go down to 259. We'll find the lab that we can do the experiment in. I've set it up in there. Well, got the materials in there, but we can move it if we need to. And then next Tuesday, after the weekend, the last 30 minutes of the class on Tuesday will be your test on chapter 1. I do the test at the end of the period, so when you finish the test, sayonara, you can go home. And I do the lab right before the test, or if we don't have a test like today, do the lab. If you finish the lab early, you can go home. You don't have to sit around waiting for everybody else to finish the lab or finish the test and then start new material or something like that. I put it at the end, so when you're through, you can leave. Okay. So, even though we're going to cover different material now, the test will be at the end of the period from 7:15 to 7:45 on Tuesday. If we finish chapter 2 by then, we'll have the chapter 2 lab, we're not going to finish chapter 2 by then. But if we get far enough into chapter 2 to do the first lab, we'll have that first lab 2 hours before that. So that'll be 5:15 to 7:15. I almost guarantee you it will not take you 2 hours to do that lab. So when you finish the lab, if you want to start the test, you can start the test. When you finish the test, bye-bye. Okay. So I always allow you 2 hours for the lab. Now this first lab, I said it last time, but I'll say it again. It's the longest, most involved lab of all term. Sorry they stick it to you on the first one. But if we need to, if we run out of time before we run out of lab, we'll finish that on Tuesday as well. Okay? But there won't be much that you have to do. But there is that. Any questions on chapter 1 before we leave it? Again, read it, study it. If you come in Tuesday with more questions, ask them. I'll be glad to try to answer that. Yes?
What does the front of your book look like?
Mine has the wind turbines.
Okay. Thanks.
Okay? Others will have dams or other things on it. You know, what does 10 have on it?
10 has
Extreme activity.
Oh yeah, a guy on some type of
blue.
yeah.
Some kid on a skateboard go down.
All right, so, but listen, there's hardly a dime's worth of difference between the editions. All it is the maintenance.
Yeah, it's a pretty big difference.
Huh?
There's a big difference.
In page numbers, but the content is the same.
Yours has a bunch of stuff in the chapter. Theirs doesn't.
Really?
Yeah.
And ours specifically says college physics, and yours says physical science. I don't know if that actually has anything to do
Now wait. Let me see that again. Wait a minute. No, wait.
Author name.
No, you have the
Get
wrong
ready.
book.
Get
That's the physics book. You need physical science. That's why I was wondering.
They told us. They're like, oh yeah, you're gonna need this right here.
Take it back, get your money back.
You can't.
No.
Once you open it, you cannot.
Hey, wait. If they sold it to you as physical science, that's a physical science book. No, that's physics.
That's physics.
That's
Don't
physics.
open it. The same one.
You have please save yourself.
Yes, it's 112.
No, they said if you buy a paperback, like last semester, because the class I was in had a paperback, they said once you open it, you can't return it.
Okay, if they sold it to you as physical science, then they made the mistake, not you. So if that's the book that's missing, are the physical science books down there? Does anyone know? Did you ask them specifically about physical
You
science?
check it?
I said we all go.
Y'all go there right now.
Are you going down there now? Are you going down there now?
You don't know
And
at all.
Thank God I didn't buy it. That was a line.
yeah, it's that's ridiculous. They sold you physics for physical science. I don't know. Now, did y'all pick them out, or did they tell you?
Yeah.
Well, that's how they have it labeled on the shelf.
Yeah, your name is on the sticker.
Visible and then.
Okay, yeah. Well, I teach physics too.
Oh, okay.
I need to go read the shelf.
Just act dumb. Hopefully they'll give you money.
It should be what?
Some people don't have to act as much. Okay. I didn't say that.
That was labeled 112.
Yeah.
PSY.
Yeah,
What's that?
PSY.
PHY is physics. PHS is physical science. It's PHS112.
I would.
Yes, that's what I think.
I would call it.
PHS 112.
Yeah.
That's what matched up.
What's that?
I got PHS 112, Physical Sciences Lab, and that was on this book.
Oh, they have it wrong then. Because that's physics, PHY. That's PHY 201 and 202.
Do you mind if we go over there?
I don't mind at all. Yeah. But I'm going to keep teaching, so what time does the bookstore close?
I think 5.
It does close at 5? Okay.
I don't.
Do we want to take a quick break and I'll go down and check? Okay. Sorry about this. Okay, when you get to the lab, folks, there's stuff sitting on the lab tables. Don't be messing with it, okay? Don't lose any of it. Otherwise, it's going to take us longer to finish. So, I'll be there shortly. I've just got to move everything.
What's the room number?
It's just right next door, 253. Now, if there's a biology class in there, wait and I'll come down. Yeah, just down the long hallway, first door on the right. Before you get to the restrooms. Log before you get to the restrooms.
I'm gonna look at your book real quick.
Okay.
Mine. Alright. I was making sure I was looking for the right one on mine.
Yeah. Are you buying it online or something?
I'm gonna rent it from Amazon.
Oh yeah, good idea.
It's $30 to rent it from Amazon.
Sounds like the winner.
And I've got Prime, so it'll be here by Monday.
Oh, super. Why didn't I pass out the loud before I'll let you go? All right. Man, they sure do use this lab. Does anyone see a plug over here? There's one. Okay. All right. Here's the lab, folks.
Hey, you're safe.
Thank you.
All right. So let me call roll. I haven't turned on the sound yet, so save that. Oh, I forgot. You didn't get one. Okay. One of the books. Okay. Let me mark the roll first. Rachel's still here. John, yeah, there you are. Okay, Chris Davis never made it in, right?
I told you.
Yeah, he wouldn't be. Okay. All right. Yale, right. Got it. Oh, yeah. Okay. Thomas, right? Okay. Still learning names and faces. Both. Okay. Sean hasn't made it in today, right?
Yes.
Okay. Justin, right there. Eric, right there. Okay. I'm remembering where you were sitting. Ashton, right there. Got it. Andrew, right there. Okay. Close to it. Chris Lynn was right here. Where do you? Oh, there you are. Okay. Hiding on me right in front of my nose. David Lockhart, we haven't seen yet, right? Okay. Chelsea made it here. Alex. Terry. Okay. You're Reese? Melvin came in. Samuel is there. Okay. You said you go by Angel, right? There you go. Yeah. All right. Lisa is here. Scotty didn't make it today, right?
No.
Okay, just a few more. Adam. Okay, got it. Ashlyn. Here. And Kedrick we haven't seen from the beginning. And Jared. Second course there. All right. Okay. Now y'all need to remember this. Anytime we make the move like this, I usually turn off my microphone, remind me to turn it back on. So I'm turning it. I thought I had stopped this thing. It's still running. So I didn't turn it on. So a lot of dead time there, folks. All right. Now, I want to do 3 laugh groups. 1, 2, 3. We're really heavy on this one. So some of you join some of those tables there. Let's see how many we got. Hold on just a second. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So 6 per table, and 2 tables will have 7. I mean tables, groups of tables. So 7 here, or yeah, here, and maybe 7 there, and 6 here. Okay? So divvy up. No. You go that way. 7 here, 7 there, 6 here.
He's talking 7.
7. This is both groups. No. These two tables are one group.
Right now it equals to 10.
7 in this, between these 2 tables. 7 between these 2 tables, and 6 here. This is going to be a lot harder laugh than I thought it was. Okay. So let's say 1, 2, 3, 4, 5. Either one you want. Okay. Still need to have some people move.
We inseparable. We've been here since day one. We can't leave each other not moving.
Come on, move somebody. I don't care. But let's get 7, 6, and 7.
I'm gonna be really. Okay, fine. I'll move.
No.
I will call some manners. Where do I need to go?
Either place. You choose. She got manners, but she has attitudes with them. Okay.
Okay, so where do I need to go?
All right. Still need 1, 2, 3, 4, 5, 6, 7, 8, 9. 2 people to move to one of these tables. Okay, 1, 2, 3, 4, 5, 6. This is good. One more down here. Or you can go here, either place. Okay, that's the fun.
See.
Okay. 2, 4, 6, 2, 4, 6, 7, 6, 7. Got it. Okay. Now,
This will be close.
okay. Now,
Hey, there we go.
each of your stations, and a station is these two, and those two. You have 3 circles at each station. Okay? Let me show you what the circles look like. 2 of the stations, the one back there and this one, have a big circle like that. Every station has a circle like this. And every station has a circle like this. Okay? Now remember, both tables make one station. All right. Now what I would like you to do is, okay, I'll have 3. You got 7, 7, and 6 people. So one person, do as it describes here. Take your circle, and if you got these, oh, and the one more. Here's your big circle. Because I only have 2 of the ways here. Here's the paper you can write on. Okay? When you have these circles, be sure to turn them down like this. It's the outside edge, the bigger edge. When you have the cup, turn it like this, bigger edge. And of course, this one, only one way to turn that way. So what you do, as described here, Part A, circles and proportional constants. Obtain 3 different sizes of cups and shared paper here, or beakers with circular bases. Trace around the bottoms to make 3 large, okay, make just 1. Make 1 circle, okay? 1 circle on a piece of paper. You got paper, okay? Then pass that one to somebody else, and somebody else makes. I want 3 circles from each group. The group with 6 people, 3 circles. Each person will do 2 circles each of a different size, okay? These, everybody will do at least 1. A few of you will do 2. But only make, okay, here's your circle. There's 3 circles. There's 1, there's 1. Okay.
Everybody makes
One circle.
Again, let me say this. Listen up. The pieces of paper there, each person draws 1 circle of one of the sizes you got in front of you. Pass that to somebody else. And you draw another circle if you're going to draw 2. But you only want each team to have 3 big circles, 3 little circles, and 3 medium circles. Each team, 3. But nobody draws the same circle twice. Okay? No, both tables. Both tables. And there's your paper. There's your paper. Use that.
on paper, good. That's got writing on it.
Yep, use the back, use the clean side. Okay? It's just that. Okay? Alright. Now, as soon as you get, each team only draws 3 circles of each side.
What's the box?
Huh? That's later.
Alright, put it
Okay.
down.
You have 9 circles.
You'll have a total of 9 circles, but don't ever draw, one person don't draw twice, okay? So,
Any size you
here, let's see if we can do something else.
Okay.
You're gonna do it wherever you want to.
Okay, okay.
What's that? Okay. Now.
Yes.
Okay. You can't put it on the same page. There's several pieces of paper here. Whatever it takes. Here you go. Okay.
Hold on. You got a medium.
Now, as soon as you got, no person will draw more than 2 circles. And they're going to be different circles. As soon as you got that, then I would say, see if you can bump back, borrow, steal one of these clear rulers. Okay? Hold it across your circle. Try to get the diameter. Okay? And measure the diameter in either millimeters or centimeters. I don't care. Millimeters or centimeters. If you do centimeters, go to the nearest tenth of a centimeter. That's all these scales. So get your best guess of the diameter of the circle.
So, okay, you got it.
You do the small, do the small.
Okay.
We're trying to figure it out.
Every person, every team is going to have 3 small circles, 3 large circles, and 3 medium circles. No two, okay, no two of the same size drawn by the same person. Okay?
6 large circles.
Huh? Okay, I said diameter. That's across the circle. We can get it right. Diameter is all the way across.
We got 2 big circles.
You got 2 big circles, we got 2 small circles.
Okay, you did 2.
Yeah, we got 2. We got 3 small circles, we got 3 big circles, so we got 2 medium circles.
You got 1, 2, I see right now. Anyone else on a medium? Okay, 1 more medium here.
We got 3 small, 1 medium, 3 large.
Good deal. No, between all of us, we got a small, that's fine. Okay. Question?
We got 3 small, 3 large.
Now.
Y'all got 3 large, right?
Okay.
We got 4 large. Hey, actually, what's in this side?
So we got 3 large.
Y'all got 3 large, we got 3 medium.
Huh? You still there? Okay. There could be anything coming out.
It's coming out.
Keep it close.
Like they're coming up.
Okay. Each person was to draw no more than 2. When you do 3, that's fine. But each team should have 3 small, 3 medium, and 3 large. Okay? Then you do your, take a ruler and find your closest element of the diameter of that circle. Yeah, it's centimeters or more. Oh, that's pretty close. Okay? Yeah.
The inside of the circle is radius, right?
The diameter is from one side to the other. That's off the middle of the circle. So, get to the nearest it's a large. You get your best guess. Okay. Now you're working as a team, right?
3 medium, 3 small, between everybody else.
Okay.
You're not the only one.
All right. Now, folks. Okay. On page 23 of your lab, that's right near the end, there's your data table. Okay? So you pick, if you drew more than 3 small circles, pick your best 3 and put your diameter. 1, 2, and 3. Okay? They may not be exactly the same. They may be pretty close. They should be pretty close. But they may not be exact. You put those 3 measures.
I see 4, but then you said
I'm getting told to shut up by him.
Hey, that's him always.
You measure.
I'll take you.
No, you won't.
If you want to do that, you can. It's not. I don't have time to be teaching anybody English.
Longest distance you can. Okay? So everybody, have you recorded your 3 small circles, 3 medium circles, 3 large circles? These are diameters, folks. Now, if one of those is way off, I would do another measurement, okay? They don't have to be the same, but they should be close. And you're working as a team. You're not working as individuals. Okay. Okay. Yeah.
I chose 2.
Yeah. To the nearest tenth of a centimeter. Good. Nearest tenth. Okay. Get other people to get all the. We're working as a team.
You got to put them on one and nine.
You got 14.
Centimeters or millimeters is what I said. Centimeters or millimeters. If the centimeters go to the nearest tenth of a centimeter. Make sure you put your units down, folks.
Alright, so you got over here?
Oh, come over here.
Not right.
Does he want us to centimeters or millimeters? Let's try to do it all growing. Okay.
The large one is
Numbers in centimeters. What is that?
Why are we doing centimeters? Measure each diameter in millimeters.
I'm right mode.
So 141.
The medium one. 91 millimeters.
The millimeters.
So that's the I got 14 exactly.
14 exactly. Okay.
Or 14.9 because there's like a little bit.
She got 14.9.
Point what?
0.9 because there's
Let me
like
see
a
it.
little.
14.9.
Basically, it says 0 to
It's on that side, so that's 13.9.
Yes, it's 41.
13.9.
So, that's why originally we got 13.
So we need to share.
It's 13.
Those are fine. No. Put down what you measure.
I
Okay?
got 14.
14. And then share that with them. Okay?
14.
You're working as a team, remember? Okay?
14? You got it?
Okay, you're working as a team. Move around, talk with each other.
I haven't measured the
You're filling in your data sheet on this side, right?
What median circle?
Yeah.
On this side? Okay, so one circle is 13, one is. So we're supposed to have 3 different sizes, right?
3 different sizes, 3 measurements with each side. Exactly.
And you got 13.9.
Or 14.
No. Do it to the nearest tenth of a centimeter.
13.9. 13.9.
Okay, what did y'all get? What y'all big circle? Y'all got 14?
Okay. Now, has every team got 9 measurements? 3 for your small, 3 for your medium, 3 for your large? Okay. Now it's time to do circumferences, which are a lot harder to do, but still doable. I want everybody to look at me and I'll show you how to do this, at least one way. Can everybody see this? All of you got your 9 diameters. Okay, you got these strings sliding around in your stations, okay? And to get a circumference, that's really hard to measure. So therefore, take your string and to the best of your ability, get it sort of tight. Don't have it running up, okay? Along there, and then separate this out like this. Okay, I didn't do a good job of that. Okay, and once you get it long, take your ruler and measure the length. Now, some of these larger ones, ruler will not do it. That's why I put meter sticks at each station too. The shorter ones you can get on the ruler. There is an art as well as a science. Okay.
everybody,
That's
like,
what we're doing right now.
Oh, you would have a little bit. A little bit more.
That's a little more.
The little circle.
No.
We
Put
gotta
it,
do ours.
You're not even.
We gotta do ours. Yeah, we gotta do ours. Oh, we
each
gotta-
person should do 2,
Oh, okay.
okay? Some of the teams with 7 should only do,
Do it.
a few of them only have 1. Wait, you don't do that, do it around the, yeah.
Centimeters?
Do it around the physical.
We gotta do it around this too. So,
44. You are using centimeters. If it's not 44 meters, I guarantee you.
Why'd you say 44 meters?
44 meters is half a football field.
No, we're centimeters.
Okay.
Yeah, it's centimeters, not millimeters. Oh, okay.
that's the
I'm
end.
going to wonder if I drive into your service bay.
I just lighted it right, so.
These would be, these right here, these look like.
That's why we use centimeters, because everything's decimal. So much easier.
That's 1 centimeter? Yeah. So 1 centimeter is a little less than half. Hey, this guy's smart right here. 1 centimeter.
Is the number already on there?
1 centimeter.
Dr. Fowler,
Yeah.
so we have to do millimeters, we can't do centimeters?
Whatever you started with, if you started with millimeters, do millimeters. If you started with centimeters, do centimeters.
Okay, so
Do
don't,
it from here down to the centimeter.
okay.
Don't be changing.
Does the whole group have to be on the same?
Oh, yeah, the whole group on the same page, same units. Otherwise, that $6 billion mistake and crashing in the water. We don't want that to happen. Don't do that. Not on my watch. Okay.
So we're writing in millimeters, guys? We're writing in meter, Paul.
Not permitted. Okay.
Okay, good deal.
So, we got 29, we ain't counted right.
I don't know. You're gonna count it. Don't they have numbers here?
So it's 29.
Okay.
Okay. 29. That was on the meeting. Yeah.
Come here. 13
We
centimeters.
got 29.
Okay, that's fine.
We got 1.
So what about the diameter? 9.
This is a meeting, right? You got 28.
Yeah, that's like everybody else is like mine with the trial.
We need one more. I just did let him do it. What about the small? I got 13.5. 13.5. And yeah, 13. Yeah.
Different trials, is that just different members of the group?
Okay. You should have done 3 circles, 3
Yeah.
people measure. The small circle, 3 people large, 3 people large.
Okay, so I'll be trial 1, he'll be trial 2.
Whoever,
Okay.
I mean, you only should have done 2 measurements yourself, so the sheriff, you're a team.
Everybody else knows.
Yes, exactly.
No, your finger now.
Always on the
Can put it on this so we can see it.
Nick Saban says teamwork is really important. It is not easy doing circumference.
Okay.
Yeah, it's not fun.
Yes, sir.
Does the ratio need a measurement?
Okay. Y'all are all doing millimeters, right? Millimeters on both sides, then when you do circumference divided by diameter.
Yeah, but the line gonna start right here. You gotta start
Yeah, but you're gonna okay. Now, if you want to wait to do your ratios, I can go on and get started with you on the second part. The most important part is to get the measurements made. But if you want to go on and do your ratios, you can. I should have been doing this.
Okay, we gotta do the ratio.
Wait, Lisa, are you doing the ratio?
And 3.3.
I'm just reaching.
Well, most pies are fixed to 8
Okay, the small circle. I don't think we got our number.
You're right, you're pretty wrong. I don't care. If we're all wrong, we all gotta be wrong. We're all right.
Are you doing the bathroom?
Okay, I'm going to put it on pause until there's another question, but please remind. All right. Has every lab, every team got your 9 diameters and your 9 circumferences? Yes?
Yes.
Okay. Some of the teams have started doing your ratios. Have all the teams started doing the ratios, or not? Some not yet. Okay. Divided by 9. Exactly. Okay. And so let me just see how your numbers are looking. Looking pretty good. Okay. Yeah, everybody's looking pretty good. All right. Now, let me tell you how to do experimental error. Okay? Everybody listening? Okay. There's several ways you can do error. Usually we do it this way. Measured minus actual. Okay? And if you'll turn back to page 15, you'll see the actual is supposed to be 3.14. So whatever your average was of those 9, hopefully all the teams got something pretty close to 3.14. Relatively close, right? No, I have 0.7, right? That's exactly how pi is defined, is the ratio of a diameter, a circumference to a diameter. So it's the measured minus this, that is your experimental error. It may be positive, it may be negative. Okay? Later we'll do things like percent error and things like this, but this one is just going to be experimental error. Okay. Everybody, what's that? If you want to, you can. But what you know, yeah, what you do is 3.1, do that minus 3.14. Yes.
Yeah.
I'll just calculate it. 3.1 minus 3.14. Huh? Point, yeah, negative, isn't it? Negative 0.04. 0.04. All right. Okay. Is everybody ready to start on the area and volume ratios? Okay. If you turn back to page 16, top of the page, part B. Okay. You'll see on some table near where you are in each team, you'll see a bunch of blocks. I want you to take one block, any block. I would say probably not a wood block. Okay. And with your ruler, measure the 3 diameters. I mean, not diameters, 3 dimensions. In 3 dimensions.
Why is this one bent?
Huh?
It's bent.
Okay, we'll use one that's not bent.
Okay.
Okay? That's one.
I'll bet every one of
What's that?
What's the element?
All right, so a single block, measure the 3 dimensions of it. Length, width, and height. Okay? No. Okay? With a single block, measure length, width, and height. Is everybody listening?
I am.
Okay. What you want to do next is do the surface area of one of the faces. That's length, side, width, right? Now, when you do the 3 measurements, they should come out really close to the same measurement, right? It's a cube. So make sure it is. If it's not, discard that one and use a different one. Yes.
So I'm doing this right? I'm doing it right? I mean, I thought we did the surface area already. Bruce?
You want to ask for a surface area?
Yeah, we did that.
What is it? How do you do it? No, that's the length. Okay? The surface area, okay? Get your block. You have a block? Okay, yeah. You measure the length of a block.
There's no meter.
And you measure the width of the block. And you measure the height of the block. Now, hopefully, they could be all about the same, but it's really a cube. Right? Okay. So, okay. I prefer to use those procedures. Again, use the centimeter or millimeters. Don't use inches.
Look at this guy as a question.
Okay? Okay. And you're working as a team, so work as a team. Okay? Okay. Wait, now. Don't. Okay. That's a length. The question is, what is the surface area? So I'm trying to draw one of these. But you got them in your hand. What is the area of one of those spaces? How do you get area? Length times width. Now, if all those dimensions are the same, it's 2.5 by 2.5. That's what you got. I don't know what you got.
Okay, 2.5 times
2.5 times.
Right. That would be the surface area of one face. How many faces does that have?
Gotta make sure it's
6. So multiply multiply that by 6. Whatever you got when you did 2. Whatever your length was, length by length.
So the surface area
No. The length is 2.5. Okay. So multiply 2.5 by 2.5, and what do you get? Add and multiply. Okay, let me see you multiply 2.5 by 2.5.
6.225.
That sounds good. Okay, but how many times 6? Whatever. Okay. Now, how do you get the volume of that small cube? Length times width times height. And if all those three are the same, 2.5 times 2.5 times 2.5, or whatever you got your measurement.
Never leave your car on the screen.
Are we rounding up?
No, that's fine. Okay. All right. Then each team, once you got one block done, gives you 4 blocks.
All right, medium block.
Huh?
Oh wait, what are we doing? Where's our
4 blocks.
You got another?
Like this. However you want to do it. Measure the length, times the width, times the height, and again calculate your surface area and calculate. Okay? Yeah, it says ratio of area to volume.
What's our medium? What's our medium? 4.
Okay? You're doing 2 by 2. 2 this way, 2 this way, 2 that way.
Oh. So this?
That is 2 by 2. You
By
got
2.
2 high 2.
Oh.
I need 2 more. Take 2 more.
Huh?
2 more.
Don't you need 4?
Yeah.
How do we pull them?
Okay?
What's the principle?
Length times width times height.
Length times width.
Now you're throwing them around on the. Okay. Lord God! You're going to distort your.
Area of.
This is the
What is it? 125?
We're not using this. All we do is measure. Length times width times height. That's fine.
He's talking to you now.
0.24.
Any questions? You doing okay?
Oh, I'm sorry. Is that right?
Larry's talking to her, freaking her out. Squirrel on top of his head.
Wait, don't.
Yeah, I heard you.
Okay, that can't be true.
We are doing
Because you can't have a smaller surface area when you have a bigger block, okay? Still now you got 30. Okay, it's 5 on the side, right? So 5 times 5 is 25. That's one place. 25 times 6.
Oh, wait, no, 75. Stop.
Of course. divide it, it comes up.
Oh, shit. Never mind.
Wait, this is the surface. It says length times width times height. What's that? 5 times 5 times 5.
25. Alright, so volume is width.
Volume is
I think it's not 50.
Keep this 3 square.
125 is volume. Divided by 150 for the 1.2. No.
Okay, so now.
Area, looks like area divided by volume.
125,000.
Now we're gonna get a lot.
Yeah, I would say go back to that table and do 3 by 3 by 3. So I'd say take those back there. Or take these two sheets, you don't need them all. Go over there and put them together. 3 by 3 by 3.
What did you say? How do you figure out volume? So that is this with a small one.
He grabbed his blocks and ran, okay. When you only got 3 by 3 by. They're all over between these two pages. No, over there. Don't get them off that table. That's theirs. I know. Yeah, they are over there. Y'all are working as a team.
That's what I'm saying.
You have to be on that.
Okay, now put all that together.
Wait, so how did you get that? How many sides did you do? Yeah, but you did how many cubes?
4 by 4. 2 by 2 by 2.
Yeah, we need all the rest of them.
Okay, you're gonna need all of them. Take them all. Oh, wait, are y'all doing the big one now?
Yeah.
You're gonna need them all. Let's lay them out that way.
No.
There you are. Run them all over the floor. Okay.
This looks like an idiot.
3D printer.
Okay, you got this.
I don't know you I can't tell what my family's sarcastic. I've known them the first year. The first time we shanked up.
I think that would work. I guess that was a jigger
My semester hates it better. Third semester it got better. But now
46.8?
oh, he lives with it. No, that lives with it. No, it's not that it got better. Somebody stopped saying something.
Here, wait. These numbers look These do not look equal to square. Yeah. Surface area and length times width.
So 2. So let's just find 2. We're good. We're good.
Yeah.
Did you square the number as well? Oh, yeah.
So these are all. So 2.5.
Right.
I'd say 10. What's your name? What's your name?
It's whipped
You got circles. You did circles there. That's what he told me to do, but he didn't know that it's the word.
So what we just square these numbers?
4.8
No,
times.
not at all.
7.8. I mean,
Those
they're
look pretty close.
That's not it.
These are the ones that don't look close. What would you use?
Yes.
So then
25, no, 25 and 25. Second. 25 and 25 is
0.769.
Okay, yeah, good. 25 and 25 is 1 face. You have 6 faces. 25 and 25 is 6.
I know 1.3.
25 and 25.
I divided 3.
But your, no, they're different because they didn't round it. Yeah, he didn't, yeah.
125 times 6.
I mean, it's the same thing, it's just not rounded.
It's like there's no way my fingerprints in
Wait, 25 by 25 is not 1 face.
625.
Yeah, that's if you round it.
Yeah.
I can't do it.
They rounded it to.
625 times 6.
Yes, but you have to count it by 6.
I rounded it, so it's 7.5, which is the same thing.
You probably already have the answer.
4.7.
Yeah.
I mean, 4.7.
Okay, so you
What's the right answer? No, he just now made the right answer, you guys.
Okay, I was about to say, that's
Just now
really-
done.
Open up to 428.
Okay. Yeah. So where's the containers? Where the containers at?
That's why.
Dr. Fowler?
Yeah.
Where are the containers?
You ready for containers? Here.
So we just work with one container?
I've got it. I'll be right back.
Yeah, this year's.
I didn't like it. It was terrible.
No.
Everybody going to?
Ratio, yes.
They had to get their water.
Actually, this is different. You can see it.
Yes, we have one project.
Did he just give up on us?
Because our country.
Listen to me.
He is old as shit.
Okay, I've done it, for 8 weeks so far. For 8 weeks. Yes, I have.
Are you here for the assignment?
Oh, I do.
Yes, ma'am.
So we're gonna do it. The machine's
Help me, please.
She's lecturing me.
This is the struggle bus, okay?
Huh?
So we don't
Struggle
take you as
bus.
much.
Oh, okay.
You're automotive?
What you gonna do? You answer the question.
Actually, it is better than it is.
I had fired up.
What about him protecting?
Hey, we'll give you a 5.
No, I know that's not wrong.
You have diesel first. I don't think it's really
No, I'm saying.
That'll get shot into the roof. Thank you.
There's a lot of bull.
I've seen
They
it.
don't have to do
What is
that.
the answer? You said where are they?
What are they?
I shot it 7.62.
Oh, it's the beginning.
Yeah, 7.62 millimeters.
Let's check.
That might.
Right.
So we get all that new shit out there.
That point now, 0.008. So wait, these are volume drive. Volume drive.
Yes.
Okay. Have all the teams finished the cubes?
Yes, sir.
Okay. Let me just get an idea what your ratios are. Pretty good. Okay. All right. Now, on the okay, each team. Now this part is a little different from the others. Okay,
This is the last.
because this is part C. So it starts on page 16 and goes to 17 and even on to 18. Okay? Now, each team has one container. This poor team here wound up with a little one. Poor things. Okay? They're little rectangular containers. Okay? Now, what you do is take it. Let me use yours if I can. And you have a meter, a ruler that, yeah, here's that. Okay. Now what I want you to do, everybody look up. Okay? The first thing it asks for is, whoops, wrong one. These are not quite straight-sided. This side is a little curved. So here's how we adjust for that. When you're doing your measures, again, use centimeters or millimeters, I don't care. I would say do the middle of the side and give your best guess, and they're also curved a little here too, so do the best guess of what the length, the width, and the height is. You might want to pull this up to get your height that way. Okay? So you see what I'm saying? Use, especially this side, the length. Use the middle of it. Not at the bottom, not at the top, but about in the middle, and that'll be a good average. Okay? Do length, width, and height to the nearest. You use centimeters only, no millimeters on this one. But use your nearest tenth of a centimeter, which will be your little millimeter. And while y'all are doing that, I'm going to be collecting the blocks. If everybody's through with the blocks, I'll start collecting. How many blocks? Are you working? Thank you.
He said inches.
This is in centimeters, so we cannot do anything.
That's what I'm saying. He said
Okay.
exercise.
Back on the bus, we're taking off of that.
Are we doing three containers?
Hey.
Yes. Yeah. Are you needing the lab? Okay, absolutely. Are we in your way? Okay, yeah. Is my computer and stuff? Oh, just right there. Yeah. Y'all can bring people in. It's not going to bother us at all. We're loud and obnoxious. That's all. Hi.
What was the width? The width is 4.
Wait, the height or the length? Wait, we didn't get the length?
Oh, 14 centimeters. The height is 30. Width and height.
What's that? Okay. Wait. Oh, I'm sorry. I should have said this. Wait, time out. Okay, it's okay. Put them anywhere you want to. The other teams, you're going to do one container, and then you're going to share data. You're not going to swap containers. Okay. So that way, unfortunately, we'll get out of here a little sooner. Sorry about that.
Everybody's doing a different container.
You just do your container. Do the measurements. Link those with them.
Everyone, so there's an extra one.
We're doing.
They got three sides.
Oh.
372.
No, they got this one. They got like water.
What?
I'm being stupid on my mom.
You keep being stupid.
It's the first time in my life.
Okay, wait. Okay. You ready? Okay. You see where you are. Now. All right. John wants complete, right? They measure it for the
Never mind.
Okay. Yeah. Okay. You finish it. Well, you're already giving it. Okay, I was going to say, just work on yours and then I'll share the data. The master container. So then.
1 second.
Okay, so what you do, you have a water container there, right? Get that, and fill it pretty close to full with water. Fill that with water, from like we're at, right? So turn off that. You did the master container first, and then the master water in it, right? Yeah. What is that mass?
That's 96.
So I would do it again, 0 to 10 first.
The container is 6.
How is it 6? How is it?
Yeah, it's a piece. He messed up.
I got it.
Yes. Mass of the water.
Well, you're looking at different angles. One person do it, that one person do the whole thing. Got it? You got to put the scale on. How are you going to do great scale so on like
What?
Okay, 29, whatever. Scale may be awful. That's why I had to do it. Open your lid. Okay.
You may hold it, you know, to begin with. Okay, someone very slowly. Now we're going to water.
Put a little bit of water.
Yeah, move the thing out of the way. Where's my track?
You don't work that.
Alright, Jeff. I got no idea what you're
What do you?
Wait.
Now, I'm pretty sure that's not a slow. I got 1.5 on I'd like to be accurate.
Not 96. What is it? 99.
Now.
I mean, I don't.
Now it's not 82.
I was up all the way out.
Okay, get the water.
Yeah, look at that. That's too much.
Get the water.
Measure.
Millimeters? A cubic millimeter?
Okay,
It's the same thing as
It's
a
99.
millimeter.
exactly.
It translates.
It's fine. It's
On
not
the
just
flow,
big.
it converts.
Bill and I would be proud.
Alright.
That's 100 like this.
Are you sure?
Y'all did it?
Yes, sir.
Okay, everybody.
We messed up.
We're trying to get back down to what we had.
Hey, wait. You don't go down to what you had. Change it and put it to
Oh wait, you're smart. Let's just move it to what I have here.
Right, you don't move it. You deal with the taser and measure the math.
So altogether, so what?
It's full right here.
Wait.
The 96.
I just saw you dumping water out there.
Oh, it's got to be all the way full.
Of course.
Oh
What?
Don't dump it. No, wait. Put it back on there where it was. That's why I gave you a container to fill.
Oh, I got you.
Really?
Now you know.
Oh my God. Yeah.
All right.
That's how you get volume.
Hey, it's laying there, right?
I have a good question.
Okay, so don't go there for the measure.
So that's mass and water.
Yeah.
It's just going to be like.
Experimental error. Okay.
Gail's got a great idea.
Okay, so this is still sitting right now. 113. It's okay, just fill it back up and then do it back up.
I got your paper wet. I'm trying to get it out of the bag.
You're being too difficult.
Mostly
Look, what we gotta, okay,
Need
what
some
we gotta
paper
do?
towels.
What we gotta do?
What have you done?
What we gotta
We're stuck. We suck.
Okay, what's wrong?
We are stuck.
do? You suck.
I got like an hour.
Hey, I got an hour drive home.
Where you live?
Where you go?
I live in Connor. Yeah, I got the
Where that's up.
phone.
Drive fast.
You know how I say it.
Okay, that's what I'm there. That's what the amount that we.
Can we take a question on this?
What's
I get
that?
it on my 19.
Yes. That's what I was going at.
But, okay. Don't leave the element to talk to you about something, okay? Now.
Not 119, man.
What is it?
111.
How have y'all done it? Finished?
Okay, so now how you want it?
Yeah, okay.
Where's the color?
Beneath the graduation.
Don't argue about it. Okay. All right.
I'm not doing it this time. How are we getting that?
Okay. All right, wait, okay. What you're trying to do, here's what I suggest. Dump water out of that, is that empty?
Okay.
Okay.
That's all I meant to know.
Okay, now, take this, that's okay, it's close enough. Okay, take this very carefully and dump it in here. It's a lot easier, it's a bigger plant.
There we go.
Six.
How about that?
No?
I had a little too much for
Hey!
I had a little too much.
What do you mean a little too much? If it was too much, it would have run over.
Look, we can just do it like this.
Okay, let me know what shop you work in, so I'll.
I worked down the floor. You're good.
All right.
I should have just stayed at my seat over there. I should have just stayed at my seat.
It's all worth it. Okay. All right. All right. The team that had the small container. Bless you, people. Okay. This is supposed to be the easy one. Okay. All right. The two teams that didn't have the small container, let me see your data. Who's got the correct
You
data?
said 119?
No. All I want is the dimension. So the teams that didn't have this, copy these down. Length. Okay. Did y'all already get them? Okay. In one of your columns, put this. Length, 9 centimeters. Width, 4 centimeters. Height, 3 centimeters. Skip 4. You can do the calculation. Number 5, mass of container, 6 grams. 6, mass of container of water, 119 grams, with several scratch outs. Okay? You do the rest of the calculation. Okay? Y'all have what? Medium? Okay. Yeah. Those with the. Okay, you two teams that have small and large. Here's the medium data. Which one? The first one? Okay. First one. Length, 14 centimeters. Width, 4 centimeters. Height, 3.2 centimeters. You calculate your volume. Mass of the container, number 5, 10.1 grams. 6, mass of container and water, 113 grams. And the rest of it, you do your own calculations. Okay, who has the... You right I'm sorry. Measured volume of water for the small one. You all have that? Measured? Did you measure this?
Yes.
Oh, that's what you're doing now. Not all. Okay, you got it? 119 milliliters.
So it's small.
For the, yeah, small one. Okay, is that why y'all were dumping out and stuff like this, trying to get the numbers to match?
That's what he was
We were
trying
just
to
trying to
do.
get it full. I don't know what he was
I'm just trying to get.
We don't speak for him.
All right, y'all are sharing data. Fine. Share data. All right. Before you leave, make sure you have all the raw data. You can go home and do the calculations, but do the raw data. Okay. Now, you have another 40 minutes, so you got plenty of time to work on this if you want to. And you're in groups, you can work together. Let's look at some of the questions here. Okay? Do the calculations it's calling for. And when you get time to turn to page 18, when you get everything else done, before you do number 6, see me.
Yes, they were the medium. They're the
Yes, what?
So this is yours.
Why you come with? Apparently thin air. There was
So you said we can do this?
You can, but let me go over the stuff you need to know. I just wanted everybody to get ready at the same place so I can talk to everybody at once.
The whole automotive class. One crease. Alright. Oh, yeah.
where?
On page 19. What is it? Okay.
Yeah, but number 11 is.
All right.
Yeah, it starts with 10.
Okay. Are y'all ready to start talking about the questions? Okay. Now, here's what everybody did the part C, which was page 16 and 17, right? Okay. When you turn to page 18, it says make a graph of the mass in grams, that's the row 7 data, and the volume in milliliters, the row 8 data. Okay? To picture the mass per unit volume ratio found in step 5. Okay? So what you do, you put the volume on the horizontal axis. Okay, the very last page in your lab is the graph page. And I'd suggest you turn it this way. It doesn't matter, you can do it like this if you want, or like this, either one. Okay? You put the volume along here. You have 3 volumes, right? That was number, row, row 7 data, right?
Yeah, max row 7, millimeters row 8.
Right. So the row 7 data will be along the horizontal scale. The mass, is that 8?
Mass of water 7.
A mass is 7. 7 goes on the vertical scale. 8, the
Measure volume of water.
measured volume of water is on the horizontal scale. Okay? You've got 3 masses, 3 volumes, right?
Yeah, that's how this works.
Wait.
Uh,
Mass
yeah.
was vertical. Mass of water was vertical, right?
yes, mass is vertical, and the
Measure volume of water.
measured volume is horizontal. Okay, and you're going from yeah, you do small, medium, large.
So make sure you go small, medium,
Okay.
large. You're small.
Wait. Now I see a fairly major problem here. Okay, you got your small mass with your large volume. That can't be.
That's it. Which row it is?
Who did the large container? What was your mass? Okay, your mass of water could not have been 38 grams. 38 grams would have been right there. This thing is all the way around. So it may have been 538. Is that right? Okay. The large container mass of water is 538, not 38. Okay?
Right here?
Yeah, 538.
Okay.
I'm guessing now. I'm guessing. Let me see. That seems way too big. Okay. Okay.
He said that's even wrong.
You were arguing with my phone.
Okay.
Yeah, I see 538 working. We're already at almost 420 and they're already full. So we're not. That's full. It has to be. Do you shut the lid or no?
Huh?
Do you shut the lid or no?
No.
Okay.
It's hard to pour the water out.
Alright, so 491.
The large one is 491 on the ground. Wait, you gotta subtract.
That's a mass of water.
That's mass of water and container. And you have to subtract off the mass of container.
So, like I said, if you guys want me to dump this out, the whole day won't be covered in water, I'll let you do it. Water is 91 for the large one.
491. You got to set 29 from 491 to get master of the water. Mass, yeah. Mass will be contained in the water.
What's the mass of the water?
Is the master container really 29?
It should be bigger than the other two.
So, then we
Is
look
it?
at the number 10 gonna change to 499.
I got 6.
Mass of water.
Okay, then now they need to pour theirs into a cylinder, right? Or
You have to redo everything. Next time we need to take like 3 hours for the lab.
None of the other labs will be this long.
Thank God.
Next lab will be really big. What?
So how do they go?
They are. Steel and iron.
So 250 plus 200.
Glass is VR. Oak is, I can sell those for 53 with. Acrylic is clear, just do that.
We'll see you on Tuesday.
What's that?
We'll see you Tuesday.
I can't hear.
We'll see you Tuesday.
See me Tuesday? Yeah, we still got a half hour.
I get up at 7. I leave my house at about 7:18 to 7:20, and I get there at about 7:28.
Cause he lives right now.
Sometimes you gotta drive out of your house.
Now we gotta redo that.
If I was you,
I'd be getting I'll be living on the roof.
Why you chose to come over here?
What, the guy who works with, he like working?
Yeah, I'm gonna have to do this.
What'd you say?
Miss,
Well,
we don't understand the crowd.
What's that?
We don't get the crowd.
Okay.
Do it.
Okay. Now,
Okay.
okay, y'all want to listen up on the graphing. Does everybody have it already?
No.
Okay. Okay, I'll need some data. There's the data. All right. Now, legal. Okay, now you have to pick, is everybody listening up on the scale?
Okay.
I think everybody's got the same ones. So it looks like to me your masses are running from 103 to 491, right? And your volumes are running from 84 to 430.
What are the massive?
Okay. Some of your calculations are not correct here, but we'll get to that. Okay. So for the first one, okay. So let's just count.
I got a question.
Hey, you guys.
So
You fill your container, right? You fill
You
your
don't
water.
know what 103?
Well, 103.
Because the numbers are not
It's a
making sense
massive.
at all.
It looks like that's the small one.
We're reading it.
Okay. All right. So what you're doing, you're going up to about 500. Okay. Let's say each one. 0, 100, 200, 300, 400, 500. 0, 100, 200, 300, 400, 500. That'll get everything in that square. So let's take the first one. Mass of 103. Well, let's do the volume first. Volume 84. So it'd be, if that's 100, 84 would be 8.4, about 4%, about quite halfway over. Then go up to 103. So that would be less than 110, so that would be somewhere right in there. Make sense? Yeah. And then the next one would be volume of 119, so that would be 100, there's 200, so it's almost 120. There's a second little mark there.
Yes. Dude, that was
Yeah, these are the mass, this is the vertical scale, this is the volume, that's the horizontal scale. Yeah, okay? And each block, big block is 100. 100, 200, 300, 400, 500. 100, 200, 300, 400, 500. So 120 would be 100 plus 2 small. 119 would just be just short of that. 135 would be between 130 and 140. See how to do it? Same way it works. Does that make sense?
So all we doing is the mass and the volume.
Yeah, you plot the mass and volume and bring me your data. Okay? So, pick your column. By the way, this thing, do your calculation. Do mass per unit volume, 105 divided by 84, and tell me how you got 2.1.
What do you think about
105 divided by 8.
Did y'all, are you the author of that? All right, this question. 105 divided by 84.
It's 1.2. It was 1.3 actually round.
Yeah. Check your calculation and mass divided by. No.
So I was not right here.
Yeah.
Yeah.
No, you're the small.
Well, I guess.
Wait, I don't understand this. That's the water. There's the water. But how in the world do you have a smaller volume here than the big one?
Because we're thinking they messed up.
Yeah, y'all, you put the same numbers here.
Yeah.
Okay? Okay, get your data, flip it. Folks?
Oh, for real?
Come on. I think I got it here. The calculator volume, 108. Big one, 372. And 179.
Tuesday.
Yeah.
Hello,
That's the agreement.
Okay.
So what is it saying here?
Chelsea, where are you trying to go? Home. Are you done?
Yeah, I think it's.
See, something is, okay, this
When I finish.
this is the medium container here.
You got medium or large?
Medium.
Yes, we have a small mass,
Yeah, but
something's
you
wrong
have
with
the
it.
No,
Way off.
they're max. This is small.
Yeah.
This is large, so they should be medium. It should be in between this and that. So they have, their water is wrong. That's what's wrong.
Yeah, the mass, something is way off.
So let's go yours back over the water.
Okay.
Okay, I'm
Right, so fine, you're gonna apply all three.
Okay. Good
So,
news,
just say
good.
I got it.
103. These individual lots counted as one.
Okay, be sure you zero the scale. You pick it up like that and make it zero off.
Look at the 10 and then those.
Be sure you zero the scale before you put the container on.
So that's how it works.
Just have everybody give an 80 on this.
What's that?
Just give everybody an 80.
So, you guys got that?
Okay,
80.
80? Okay, out of 25, I don't think so.
So we still gotta do.
Yes, yours is
Maybe.
20.
28.
I would suggest you can't try that.
I'm just, listen.
Wait, they want you four like that.
Since you guys are sitting high level with this, tell me when it's full. Completely, like all the way flat full. You can put more water in there. That's fine. You can go a bit, put it down on it. Keep that either. So it's like 187.
All right.
We're only off by 100 grams. You guys are medium?
Yeah.
Something like that. That doesn't make sense now.
Can we give the last team now?
No, I would say let's bring them in because we got to show the correct data.
Now yours is bigger than this.
So take them home. You can start. Okay, everybody, I'd suggest that you start working on your questions. You can do results on page 19. You can do problems on page 20 and 21. And come back Tuesday and we'll straighten out some of the data.
Okay, that sounds like. Yeah, it's a little too confusing.
It's all confusing, none of it's matching.
Huh?
That's all confusing, none of it's matching.
I was saying those numbers.
I'm not, don't worry about it. She said, don't worry about it.
I mean, I'm not sure. Yes, first line.
Sounds good. Hey, somebody should get in the cup. Hey, get in the cup.
Good job, y'all.
Yeah.
Oh, that's probably what it is.
And
And
probably-
I'm sitting here trying to.
You can do those at home. If you have questions, bring
I'm
them.
gonna do good, guys. Woo! Jump.
Just wait. No,
Hey, the good thing is that we don't have no poor guy, did you? Nah, that's not good. They didn't get this class. That's probably why we didn't, but
yeah. Yeah, just put it on that panel right there, you see, right in front of it, right there. Good, thank you.
Mr. Bowles, you said on the sheet of paper you wanted to write who we wanted to ask you about.
Yeah,
You wanted a name, phone number.
and preferred email if it's not your, lost email.
Now, another question. My essay is, well, not an essay. My major is automation and robotics.
Okay?
How can I apply that to physics?
Okay.
Because if not that, I'm.
Say again, automation
And robotics.
Okay. First reaction to this is say, ask Nancy. Okay, but I bet she can give you an earful. But just thinking, what you have, for instance, you have your robotics picking up something, moving it somewhere else. Okay. Physics involved with that is how much weight is that you're trying to lift, with how much of a writing arm do you have here? There may be too much torque on it to support that. You may break your machinery. So that would be an application of physics to something like that. I mean, that's just one. So I bet you come up with dozens like that. So but that's one. I mean, you don't have to write related to your major, but if you wanted to, I bet you that's going to be in there. Now, when you say automation, I think the robotic part probably would have a bit more direct link to the physics, because you have to make sure you're within the tolerances of your machinery, that you're not going to break something trying to lift something too big. And then also your speed at which you do things. That's right what we're talking about, velocities. Yeah. So yeah, there's a lot of pretty good correlations there. Does that help any? I don't know.
Yeah, but I think I might pick up my narrow my habit down more.
Yeah.
I'll go with the IQ.
Yeah, he's always said,
Yeah.
As long as no one else is picking on it.
I hope
I
so.
can't remember if they have or not. All right, good, thank you.
You have a safe ride home. Mr.
All right, thank you. You do too.
Oh my goodness gracious.